Current AI agents communicate primarily through plain text. It's a highly functional format for developers, operating much like the MS-DOS era of early computing. But mass-market applications require visual, actionable interfaces, a graphical era similar to the transition to Mac and Windows. This diagram shows the standard HTTP paradigm. A client node sends a single request, and the server returns a complete response payload. But place an AI agent behind that architecture, and the cycle fractures. Erratic, continuous data streams from the server overwhelm the client. AI agents operate as long-running entities. They execute multiple steps, require mid-run steering from the user, and demand constant reconnections if the stream drops. They are also non-deterministic. A single agent output might simultaneously contain structured JSON logic for an application state, alongside unstructured text meant for the user to read. To map this varied, overlapping output to user-facing applications, developers use a structural framework known as the Generative UI spectrum. It defines how much control you maintain over the interface versus how much autonomy you grant the agent. Forcing a modern agent to communicate through a traditional REST API requires engineers to write highly brittle, unscalable glue code. Scaling an agentic application requires abandoning the request and response loop entirely in favor of event-driven middleware. This diagram illustrates the base three-tier architecture required for agentic apps. At the top is the backend, running on a framework like FastAPI where your agent lives. At the bottom is the React frontend. Between them sits the Copilot runtime, operating as the critical middleware. Zooming in on the connections between these tiers, we find the protocol triangle. The Model Context Protocol, or MCP, connects agents to their tools. Agent to Agent, or A2A, connects multiple models together. We will focus on the AGUI connective layer, bridging the backend and frontend blocks, managing a continuous, bidirectional data flow. AGUI is an open, framework-agnostic standard. It relies on an event-based system designed specifically to handle the unpredictability of AI interfaces. Instead of waiting for a complete payload to finish generating, an agent using AGUI emits granular output events the millisecond they occur. The backend broadcasts specific signals like a run starting, a tool being called, or a token being streamed. The Copilot runtime intercepts these streams on port 4002. It acts as a registry, actively managing the events and mapping a specific agent ID to the correct backend endpoint before routing the data to the user. This registry creates a strict abstraction layer. Because the React component only targets a logical agent ID rather than a hard-coded URL, you can swap the backend from a LangChain OpenAI implementation to a Google Gemini agent by updating the mapping in the runtime. The most rigid implementation on the generative UI spectrum is controlled GenUI. It sits on the far left, prioritizing strict pixel-perfect design over agent autonomy. You provide the agent with a fixed toolbox of custom visual components. The agent analyzes the user's prompt, decides which tool to use, and fills it with data. The developer retains total control over the look and feel. In React, this is achieved using the use component hook. It takes 4 arguments: the name of the tool, a precise description of when to use it, the strict parameters it requires, and the render function that dictates the final UI. This circular workflow diagram traces the 6-step AUI process in real time. The front end registers a component. The system converts it to a standard tool definition. AGUI registers it. The agent evaluates its tools, triggers a call, and the SDK maps that call back to the designated React component. Focusing tightly on the parameters step, we see the Zod schema filter parsing the incoming JSON payload. It acts as a strict validation layer. If the agent hallucinates a data type, the schema rejects the malformed variable, ensuring only verified data is injected into the UI wireframe. When the validated front-end tool call executes, the AGUI protocol steps in and actively halts the backend agent's execution loop. The system pauses the AI's internal processing to prioritize rendering the React UI for the user. Controlled UI guarantees strict brand compliance and prevents UI hallucinations. However, the developer effort scales linearly with the product surface. If an application requires 200 unique agent capabilities, engineers must handcraft and maintain 200 dedicated components. To solve that scaling bottleneck, declarative generative UI sits firmly in the middle of the spectrum, balancing developer control with agent autonomy. This declarative approach is driven by A2UI, the Agent-to-UI specification, an open standard developed by Google. Instead of building massive, monolithic views for every possible task, you provide the agent with a catalog of reusable UI building blocks. The component catalog strictly separates two concerns. First, the platform-agnostic definitions, which tell the agent what the block does. Second, the platform-specific renderers, which dictate exactly how that block is styled on the front end. This animation shows the real-time assembly process. The agent selects blocks from the JSON component catalog and dynamically assembles them into a structured UI schema. Once the wireframe is built, the runtime populates it with live data bindings. Developers can implement this using fixed schemas, where the layout is hard-coded and the agent only injects the runtime data. Alternatively, they can use dynamic schemas, giving the agent full permission to architect the layout from scratch based on the user's specific request. Declarative Gen UI removes the linear developer bottleneck. By delegating assembly logic to the agent, applications can address specialized long-tail layout needs, like niche data tables or specific internal tool views, without requiring unique component development for every scenario. Moving to the far right of the spectrum, we reach open-ended generative UI. Here, all pre-registered component constraints are removed. This diagram illustrates the sandboxed double iframe architecture of MCP apps. By isolating JSON RPC communication between a host frontend and an embedded view, you can securely embed fully functional third-party platforms directly into the user's chat interface. The alternative to embedding apps is fully open generation. By setting a single Boolean flag to true on the runtime, you permit the agent to bypass predefined components entirely, writing and executing arbitrary HTML and JavaScript from scratch. Granting an agent boundless UI capabilities allows for hyper-custom user experiences, but those experiences come with severe trade-offs. The high token compute costs, latency delays, and visual unpredictability mean this approach is best reserved for the late long tail of highly exploratory prompts. The final evolution of generative UI moves beyond the boundaries of the chat window entirely, establishing canvas applications. The architectural goal is to elevate the AI from a disconnected chatbot bolted onto the side of a web page into a native application entity that continuously shares live state with the user. This requires front-end tool calls. You grant the back-end agent permission to execute real, asynchronous functions directly in the user's React document object model, allowing the AI to open panels, trigger animations, or navigate the application autonomously. To prevent the UI and the agent's memory from drifting apart, the architecture implements bidirectional state synchronization. This continuous streaming replaces traditional manual API data polling. This split-screen visualization demonstrates the use agent hook in action. When the user flips a switch on the left, the update instantly propagates to a Boolean value within the backend JSON state tree on the right. When the agent updates a variable, the frontend reacts identically to standard React state. If the user edits the UI at the exact same millisecond the backend agent attempts a tool update, the AGUI middleware operates as the traffic controller, automatically resolving the data conflicts. This synchronization ensures the user and the agent operate on the same data structures in real time. The agent can now react to a visual interaction, like a user selecting a chart segment, before a single word is typed into a chat window. There is no single correct approach to generative UI. Each segment of the spectrum serves a distinct engineering purpose. Looking at this composite dashboard schematic, we can see how robust applications mix and match these patterns. A rigid, pixel-perfect UI chart utilizes the controlled approach. The dynamically assembled report block relies on declarative schemas. The sandboxed third-party tool operates open-ended. All three are linked directly to a central shared state hub. Because these patterns run on the open-source AGUI protocol, these mixed interface models integrate cleanly across the broader agentic ecosystem. This interactivity layer is only the beginning of the production stack. For these applications to scale, we must solve for the technical friction created by non-deterministic, on-demand interfaces. The first hurdle is persistence. Because the UI is often generated or assembled at runtime, the system must reliably store the exact state tree and layout schema. Without this, the interface would reset or regenerate inconsistently every time a user refreshes their session. Next is the insight layer. Traditional telemetry only tracks clicks on hard-coded buttons. In a generative environment, we need new tools to analyze what the agent actually rendered and how those non-deterministic paths affected the user success rate. Finally, these insights must feed into a self-improvement loop. By tracking where an agent-generated UI failed to satisfy a user, developers can tune the underlying prompts to refine future generations across the entire spectrum. Mastering the trade-offs of the generative UI spectrum and adopting event-driven protocols to support them is the mandatory first step for engineers tasked with building the autonomous application architectures of the next decade.